There are also a couple of disadvantages, as you may have noticed already. First of all, in terms of laptops, there are no sockets. So if you have a poor battery, then you're more or less stuck for the quizzes. That's not a nice idea. The other thing is that for the actual quiz, if everybody shows up, then I think we're 1, 2, 4, 6, 8, 1, 2, 3, 4, 5, 6. Then we're sort of completely full, or almost. And then it is hard not to cheat if you are as close to each other as you are now. So I'm thinking about changing the setup to basically, let's say, change the Wednesdays with the Fridays. So that would mean that the quizzes would be on Wednesday, hour 7. One advantage would be that I didn't check, but I think that in Gemini we have sockets available, so that's already way easier. It's also a bit of a bigger room, so that will give you some room to move and need a little bit less work to try make sure that you don't eat too much. Yes?
On Wednesday, the last 2 hours were scheduled also in the auditorium. The first 2 hours are...
yeah, but in 6, I think.
Oh.
And that one is at least way bigger. Well, I'll have a look later to see if that is, how bad that is. I already tried to, because I found that there was somebody else in hours 7 and 8 in the Gemini hall. So there I've already suggested, because that would be more convenient anyhow, for them to change with the auditorium. So you could simply stay there, it would be way easier. I haven't heard about that just yet, but that would be at least a solution. So for now, we keep it as is and we just we see how it goes, but I'm trying to change this to Wednesday. We'll have to decide exactly when and how that is going to happen, but you know, I think nobody else is getting into any extra trouble because of the change. And also the lecturing could be done more here, which is better. Although here, for some reason, there is no microphone, so I'm doing this without any backup. I think for the room itself, this is not so much of a problem, but I'm taking, and I'm not so sure if my laptop is also going to be quite reasonable. But well, we'll see how that goes. So in let's say 45 minutes or so, in the next hour, what we'll do is try the quiz to see if it works. It's a practice quiz anyhow, so we just get acquainted with all the stuff on Moodle and how it works and if it works. And all the stuff that needs to be repaired for the first true quiz can then be done in time. Okay, so first a little bit of lecture stuff. Normally I would just be standing there taking questions. I'd be happy to take any questions if you have some right now. Anybody? We're just starting, so there can't be too many questions at this point. But let me take you through the hypothesis testing part. It's important to realize, I think, that what I'm trying to do throughout the course is get us through statistical testing without doing, well, basically any kind of statistics. And for, let's say, 95% of the students, this is an improvement, in the sense that you don't have to go through all the mathematical details to figure out exactly what's going on. There's perhaps 1 in 20 out there who prefers to learn through the math. If you are one of those, let me know. There is quite a few materials online as well that will give you the mathematical background if you want. But for most of the things that we're going to do, it's really not necessary to know the mathematical details. But you do have to know, let's say, the general gist of the arguments. I have the screencast from the last lecture, the previous lecture, online. And I have one version of our data online. It's not yet exactly complete. We have 145 or so. So we're still 20 or so short. If you haven't delivered the survey data, please do. The link will still work. Let's say over the weekend or so, I'll simply check with all the student numbers who has already filed and who hasn't. Just make sure that we have enough data to work with. But already now you have, let's say, the first 145 cases that you can see online. And I think most, not all, but most of the analysis that we'll tackle, we will do on our own data. And we'll see how that goes. Okay, so this was what we're up to. This is what data looks like in Stata or in Excel or in any kind of spreadsheet. And and then you have to do something with it to figure out what's going on in the data. This one I also showed you. Normally, that's what I already said, we have an hour of Q&A, not now. And this is what we're going through. We have Stata already. You've checked the Moodle site, or the Encore site, or whatever you like to call it. And I tried to make the claim that all the stuff that we're going to do, or almost all, is about relations between two or more variables. So there are some variables that you want to use to predict another one from. And now we get the general logic behind hypothesis testing. And the good thing about that is there are many, many statistical tests, way more than we'll actually but the good thing about the statistical tests is they're all the same in the sense that they have all the same format. And if you understand the format, then it's way easier to basically understand any kind of test without even knowing what the mathematics is. So the good news about that is that, let's say, given that you understand this general logic, you can relatively easily read all kinds of statistical tests. Okay, so here goes. First, stuff that you need to do on your own. That is go through a couple of standard commands in Stata. None of these commands do, let's say, really complicated stuff, but you do need to know how they work. Here they are. For instance, this one, you saw that last time already. It's called tab, or tabulate. It is a frequency distribution of a variable that you have sum. You already saw that. It gives you a summary, the mean of a variable, and the minimum and the maximum, and so on. Des, or describe, gives you an overview of all the variables in your data set. Codebook gives you a more complete overview of all the variables in your data set. And perhaps the only one that is a bit less standard, the command gen for generate. With this you can create new variables in your data. So if for some reason you want to create, let's say, age squared, then you can simply do it like this, generate age squared equal to, and then age times age. We'll see that a couple times, also in the assignments as well. There's a lot of annotated output online and a couple of screencasts from other people than me who show you these basic things and also show you some extra things that you can do along these lines. And besides this, there are a couple of things that you need to know in the, let's say, in the graph department. There are a couple of standard graphs that you have this here, yeah, that I'll show you in a minute. First, these commands that I showed you, tab, describe, and sum. Tab will just give you this. An overview here for age. We have 3 persons who are 18, 29 who are 19, and so on. By the way, this is data from last year, so this is not our data just yet. Over there, describe gives you a list of everything that's in the data. Summarize age. Here you can see some other things about the same variable, and if you just do that, you get 103 observations. The minimum is 18, the maximum is 33, and so on. So it's an easy way to get a bit of an overview of the stuff that we have. Then standard graphs. First one on top, a histogram. A bar chart, basically, of here on the horizontal axis age, and here how often that occurs. And there are a couple of things that you need to realize here. The D, for instance, there is for discrete. If you don't type the D, then what Stata will do is try to figure out roughly how many bars that you need, simply by guessing. Usually that's quite crude, and if you know that you have something that has discrete values here, it's easier to suggest that, then you simply get bars for all the values that you have. Here a box plot, looks like that, graph box, and then whatever variable that you need, and a scatter plot if you want to have a scatter plot for 2 variables, y and x, scatter y, x, and then you get something that looks like this. Okay, all this is in chapter 5 of the book. It's all relatively straightforward. Every once in a while, it's useful to have a look at your data to see what's in there, also to see what weird stuff might be in there. For instance, in the data that we have now, I think there's a variable in there that's called time spent. And there you see that there are quite a few people around who have really large values there, time spent in the hours even, or days. Could be true if you leave open your computer and then return after 1.5 days and finish the survey, perhaps, but a couple of strange things are happening there. And looking at these plots is a useful way to figure out where they are. Okay, so what did I want to say here? Oh yeah. The more detailed summary that you have here, the soccer score case, here we have 147, so this is actually our data. We had 7 questions about soccer, multiple choice questions that you could answer correct or not. Here you see the average score, on average 4.3 questions were answered correctly. And here in the details, one of the things that you can see here is at this 50% level, there you see what's called the median. Half of the numbers is below that number and the other half is above. Very often a nice summary statistic, and also something else that you might know, the mode, that is the number that occurs most frequently. And here you see, okay, 1, 3, 15, 20, 40, so number 5 is occurring the most, so 5 is the modal answer. So again, this gives you a couple of summary statistics about the stuff that we have in the data. Okay, all this we typically need before we do the actual complicated stuff, so to speak. And all the things that I showed already here are all, let's say, ways to find where the middle point of the distribution is. So these graphs, those are what typically called a distribution, in Dutch, verdeling. And if you want to convey to somebody else without showing the graph, okay, what does it look like? Well, one thing that you could do is say, okay, it's about here, here's the middle, and it's about this y. So we're looking for ways to translate where the middle is and what y means. Well, I already showed you a couple. The mode, the median, the mean. Mean is most often used, and we'll see later exactly why that is. But all these would work. Yeah, another one would be you take the maximum, you subtract the minimum, and then you pinpoint halfway. It would also be considered somewhere in the middle. And you see here, well, typically that these kind of things, where is the middle, are what we use when you compare groups of people. For instance, if you want to know on the soccer score variable, the average was 4.3, and we want to compare, let's say, boys versus girls. Who is scoring higher on that soccer score? Well, what we compare is the mean across the two groups. So that would be here we have the distribution for the girls. There's a middle point somewhere over there. Here we have the distribution for the guys. There's also a middle point over there, and we compare that middle point. Now, it's easy to forget that we take the mean to compare those two later on all the time. And we'll see that there is a reason for it, but it's not obvious why we should do that up front. And there are, in fact, quite a few examples where you do not take means to compare groups. Anybody who knows an example, you want to compare who scores higher on something, and we're comparing groups. And now we're looking for a case where we're not comparing means. Normally you would say, who's smarter on average? That on average is always behind it. Where do we typically not look for averages?
High scores?
Yeah, high scores for what? So we're comparing groups?
Yeah, females and males, for example, for a game.
Yeah, when we look for the highest score, because that's only one of the persons in a group.
Yeah,
So we need something where we want to compare groups. Yes?
Which group has the person with the highest score?
Yeah, okay. Okay. And yeah, it's actually quite close to what I'm aiming for.
Extreme values? Because if you have some extreme values that you have the mean.
Yeah, so all these suggestions are okay in the sense that, yeah, of course, if you're looking for the extreme of the distribution, that is indeed what I'm talking about. But in which cases would you actually use that? Collective work of the group? There's only one thing to do? Okay. Not exactly what I was aiming for here. One thing that you would typically have in all kinds of contests, who can play soccer better, the Netherlands or Germany? What we don't do is average out. Right? So everybody plays soccer in both countries, and then we check how good they are, and then we look at where the mean is, and say, oh, on average, the Dutch are a little bit better than the Germans. Then you don't do it. You look for, okay, who's best here? You take the best 11, we compare them with the best 11 from some other group, and then we see who will beat the other one. Or we're trying to figure out who's the best at chess, computers or humans. What are we going to do? Average out all computers and average out all humans? No, we're going to check, okay, our best human, how well is that person performing against the best computer that we have? But there are quite a few cases where these comparisons are not across the means. But for all practical purposes that we are going to consider, we will see that the mean is the only thing to go by. And there's a statistical reason for it. So these kinds of exceptions, in contests, for instance, and there are quite a few other ones as well, are indeed, in our case, exceptions, because we will look at differences in the middle part. Okay, that's what I said. Now, then, something else. Looks like separate topics all the time, but in the end, I hope that everything will come together. An easy thing to remember is the sampling part is easy. If we have a sample, we have data from you, and we want to calculate on the data, that's easy. There is no statistics, no nothing involved, just some calculation. The inference part, we're trying to draw conclusions about, let's say, the general population that is a bit larger. That's the difficult part. So all the statistical stuff, distributions and probabilities and cumulative distributions, all these kind of things, that only plays a role when you want to know something about the population. The sample part is easy. So sample, there's a little part usually from the population as a whole, and getting from this to there is called statistical inference. And the complicated stuff only begins when you want to do that. Okay. One example here. I think a year ago or so, there was a program, what we call it, I think Keuringsdienst online, where they checked for what's called analog cheese. I don't know if you know what analog cheese is, but analog cheese looks like cheese, it feels like cheese to the touch and in your mouth, but actually it is a combination of starch and palm oil. And the two main differences with real cheese are, first, the taste. If you taste it, then it doesn't taste like cheese, it tastes like nothing. And the more important difference is it's way, way cheaper than actual cheese. So what many pizza makers do, if you get a frozen pizza, or actually a non-frozen one, the slivers that you see on the pizza that you think are cheese are in fact not cheese at all. They are analog cheese, some weird concoction that they created in a factory for you. And they add a little bit of cheese here and there just for the taste. That's for them way cheaper, and you could argue, is that illegal? You have to write that on the package, but they actually do. They write on the package, there is palm oil in there, and there's starch in there, which is true. It would be in a pizza even if no cheese was there at all. And they also say, yeah, there is also cheese there. It's a tiny little bit, but you know, there is some cheese. So this is sort of cheating. And what they did was they sampled, let's assume they sampled randomly from a supermarket all the stuff where cheese was supposed to be in, and they checked, is there analog cheese in there? Forget about how that actually went. They find 45% of the cases there we had analog cheese on the pizza and no real cheese. Now, they had only a sample of 11 products, and they found 5. 5 out of 11 is 45%. That's the sample. If I want to calculate on the sample, easy. You know, 5 out of 11, you can do that on the calculator. It's 45%. Nothing else to do there. The other thing is, now I want to say something about the supermarket as a whole. This is a random sample. What would my confidence interval be? And there was actually a question like this also in the survey. So think for a while. This is easily done, by the way, simply in your head, if you know what the rule of thumb is. 5 out of 11, that's what we find. I want to conclude something about the supermarket. A confidence interval, I am reasonably sure that, let's say, the real percentage in the whole of the supermarket lies between what? A, 40 to 50, 32 to 58, 25 to 65, 50 to 75, or 9 to 81. Think for a minute. Who thinks A? 40 to 50? B? C? D? Oh, really wide? And and E, do nothing. Okay, distributed sort of evenly, and quite a group thinking not much, and it's also difficult to have an intuition for these kind of things if you don't know what to look for. But the rule is actually quite simple. The width of the confidence interval, if you have something like this, is 1 over square root n, where n is the sample size. So that's, it's called the 1 over square root n rule. Not very original, but here n is 11, you take the square root, that's 1 over 3 and a bit or so. If you do the math, then you end up with 45, let's say plus or minus 30%. So this is roughly what you can expect. Yeah, with a sample of only 11, you really get a quite wide interval from all the way from 15 to 75%. And we had something similar in the actual survey, where we did something like this. This is the story about the ANWB, the Dutch Road Assistance Club. They checked car shops, they find 10 out of 25, so 40% did not correctly repair a car. 10 out of 25, we're assuming random sampling, so all that is fine. 40% is my best guess if I have nothing else. 1 over square root n, 1 over square root of 25, that's 20%, so 20 percentage points. So the confidence interval, I'm reasonably certain that the true percentage will lie between, would be 40 minus 20 to 40 plus 20. So that 1 over square root n rule will tell you quite fast what the good confidence interval is. And as you can see, this is the distribution from the answers from the actual survey as I have it up to now. Most of you think that it's the one in the middle. And 23% actually was correct in guessing that this is the right answer. So, sampling, that's the easy bit. Inference about the population as a whole, here still the easy bit, but the more complicated stuff will actually fall. Okay, now the logic of statistical hypothesis testing, and the first thing that I want to do is simply show you what the tests look like, so that you get acquainted with what you get spit back at you by Stata. So here, first, I'll just show it that you remember that we've seen this before. We have different kinds of variables. The important ones are categorical ones, where you have, how do you go to the university? By boat, by train, by car, by bike. There is no order in those. Or interval, where you have a defined set of differences. Okay, so here goes. Categorical by categorical. I showed this example before, male, female, and here we have, actually there is an order in there, but let's suppose that I'm not so much interested in that. The thing to do would be a chi-square test. We'll get into details exactly what that is doing later on, but what you get back is something like this. A crosstab, male or female, over there, and would you consider yourself better than average or less than average? There are 5 categories, but the first one, nobody feels that he or she is far below average, obviously. And here you see the numbers that you find back. So the first bit that you get back at you is simply counting on the sample. How many cases do we have in the different cells of the matrix? Nothing complicated. And here you see the more complicated stuff. And in the end, you get something that looks like this. That is typically representing PR for probability and a number behind it. Okay, so the thing to notice here is that also for this one and for all the tests that we will see, there will be a probability in the end that is given to you, and that's the thing that we need to focus on. Here another one where we have 2 categories, male and female again, let's see, yes, and the estimate of future income. Estimate of future income, that was actually an interval variable, it varied from close to nothing to a couple thousand per month. By the way, I do think that you are quite optimistic in terms of what you are going to make. Well, I hope I'm wrong. So again, same thing. The test is now different. It's not a chi-square test, but it's called t-test. Again, first you get some math back. The math is going on the sample. Easy. Group 0, 61 observations with a mean of 7.5. Group 1, 30 observations with a mean of 7. And a lot of other stuff that's calculated on the sample. Nothing to worry about. in the end, here below, in a couple of places, you see that probability coming back again. Actually, here in 3 places. We'll worry about that later on, but again, you see, you get a probability back. Same thing. And you can understand this even if you do not know exactly what the test is. Final example. Interval by interval. Now we have 2 interval variables. One would be age, and the other one would be the estimate of net income. There, it's a bit more complicated, because here you have to really look hard, and you won't find it for that probability. The PR is not in the output. But the thing that you're aiming for, the correlation over there, and that number here is actually the probability that we're looking for. So you have to know for this one where that number that we need is, but it is in the output, and it's right over there. Okay, so this is one example of, there are 3 examples where you see that the output is always the same, and aiming in the end for a probability. There you have it. All probabilities that in the end you find back. Yeah, and there's another one that's a bit more complicated actually. If we have one thing that we want to predict, as in the Netflix example, with a bucket load of predictors, and only 4, then, or 3 actually, there's also something that represents a probability, and it's over there. We get into details about all the stuff that's around here, but here I just want to make sure that you see that there is an actual probability there, and then something that you can test right after you've done this analysis. Again, the probability that you get back. So even if you have no clue what this test is, you'll see that the probability in the end will show up. Okay, that's the second part of the story. Now on to distributions. First, an example of a true empirical distribution, not the guesses that you gave, but the real distribution of incomes that we had in the Netherlands 2 years ago or so. Looks like this. Let's see, we have the slide itself above here is in Dutch. Average here would be 33,000. Please compare this also with the numbers that you gave. That's the average. In all likelihood, you will be a bit more to the right, so you will earn a little bit more than what is average in the end. We see here 4.7, so let's say 5% of the people is actually earning more than 72,000 euros per year in terms of income that they can actually spend. Just to give you an idea what that looks like. The mode here, what is the income that occurs most often? That's 20K per year. The median, 50% is below it, 50% is above it, that's 29K. And here the mean, the average would be 33K per year. So one thing to notice, first of all, is that here you see that these numbers need not be the same. They can be, but they need not be. And the rest is that, in principle, this can be seen, let's say, as a summary of all the numbers that you have in your data. And you can do all kinds of calculations on this if you wanted to. Then, besides the mean, I didn't consider the spread of the distribution just yet. How wide is that thing? So the first question is about where is it? Where is the middle? Ah, there. And how wide is it? A couple of measures that we need to consider. The maximum minus the minimum. Okay, it's running from here to there, and that's pretty much it. The other one here, if you want to be a little bit more, let's say, dependent on where the middle part of the thing is, let's see where we are past 25%, stop there. And then let's see where we are past 75%, and let's stop there. So the bulk of the stuff that is in the middle is right here. That's another measure for the spread. And the one that we'll see most often is what is called the standard, excuse me. Could you stop the talking, please? It's a standard deviation. We'll talk about that a little bit later on. Also a measure for how wide the thing is given where the middle is. Okay, all a big run-up to what we would be willing to do here. The main thing to understand is if we would have the empirical distribution for everybody, as we had here, then again, all calculations would be easy. You know exactly where everybody is, what everybody scores, how many people have more than this, how many people have less than that. All that would be a straightforward calculation. Nothing to make a big fuss about, because we have the data. Typically, we don't. you run an experiment, you ask for 100, for 200 people, they are representative of something bigger, so you have only a small subset. Here too, you are sort of, let's say, representative for all students at QUE, for instance, so we have something in the sample, but not the whole population. So now what? Well, first, let's see at what the empirical distribution looks like. This is for the group of last year. If you look at what you think that you're going to earn. So here, first, I changed the actual values from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all up to 8 to 15, to the midpoints of the numbers that you actually chose. So number 1, that's 500, number 2, that's 1250, and so on, all the way to, what is it, 15,000 if you are, or if you feel that you will end up in the category all the way to the right. And then we'll see, in this case, well, here the median is 3750 per month. That is, let's say, half of you is below it, the other half is above. The mean is 4,500. Oh man, I really hope that you're right. But we'll see about that. And a couple of people, by the way, said no clue and were removed from this question. So first, what you see here is that this is one way to restructure your data in such a way that you can give some more meaning to it. You have a graph there that shows the distribution and a little bit of info about what the empirical distribution in the sample looks like. All right, here we have it. Okay, I don't know what that is. Never mind. Okay, some more. So here you see, I just took a random subset of other data points, sorry, of other variables in the data here. And what you typically see is they can take on any shape and nothing that looks familiar in the sense that you could compare it to you know, a bell curve or something else that we might know. So we have to deal with that. Almost looks bell curve, perhaps, but most of them, well, for instance, that one, totally not. So you have to consider what to do next if there is nothing that you can compare it to. So, besides, where were we? We have something about where is the middle of that thing, how wide is it, and then you want to say something about is it tilted towards the left or the right. Tilted, another word for that, or let's say the true word for that in statistical terms is called skewness. And I must admit myself that I always mess up what is left skewed and right skewed. Here you see it in the correct way. So I always mess up because, you know, standing like this, tilted towards the right is left skewed. Okay? And the other way around, tilted towards the left is right skewed. Skewed is sort of pushed down a little bit. And skewness is also something that you can measure on the distribution. So if I want to tell you what the distribution is looking like without giving you the actual graph, I'm saying, okay, the middle is about here, it's spread about like that, and it's tilted in that direction. And if you give a number with that, then you can also say something about how strong it is tilting either to the left or to the right. Typically with skewness, if you read a book about it, then you will often also see kurtosis, but we'll skip the kurtosis. Okay, so again, all this is meant to be able to do something with these data. So we're trying to summarize and we're trying not to lose too many information. You can start with the data itself. I have a long column of numbers, that's one variable, your estimates for income. That is my data. I can make a graph or tab the frequencies, that's sort of shorthand. So we have 15 categories of income. I can simply give you the numbers. How many people are there in each and every category? That's the same data compressed, and I've lost nothing. Nothing, because all the data points are still there. I can reconstruct the data if I want. I can show you a graph, which is more or less the same thing. It's a bit hard to figure out how many cases there exactly are over there, but still, in principle, all the information is in there. And with the means, the mode, the median, the skewness, the shape, and so on, all these kind of things, what we're trying to do is somehow summarize the data in such a way that, you know, there's nothing to do about it that will actually save all the information. One thing would be, aha, I just say, let's summarize the data just by the mean. Well, that's a really crude approximation. Then, okay, the mean, and it's about this wide, it's a bit better. The mean is about this wide, and it's somewhat tilted to this direction, again a little bit better. And what we need to figure out is, let's say, how much of these kind of things we need before we can actually do the calculation. Okay, some theoretical distributions, and we're not going to consider very many, but you need to at least know a couple. This is the standard coin flip example. So you have a probability of 0.5 for heads, a probability of 0.5 for tails, and you can do the math trying to figure out if I'm throwing a coin 10 times and flipping a coin 10 times, how likely is it that 8 or more heads if the coin is flipped. Okay, all of that is pretty standard, just a mathematical exercise. Here you see it. In 50 throws, the probability of X heads is, that number, assuming that the coin is fair. So if I have a theoretical distribution, the good news about that is that will be nice, because then I can run my calculations on it. So we're trying to figure out how to get away from, okay, if I have a theoretical distribution, I can do the math. But I have an empirical one, and I actually want to figure out, okay, in the empirical distributions, is there something that I can relate to a theoretical distribution? Because then I can do the math. Okay, there are quite a few more. This one is the most well-known, I guess, the normal distribution. Uniform, everything is equally likely, and quite a few other ones. So, it gets more difficult by the minute, but the principle is all these simply have a mathematical formula. And if you want to do some calculations on these kind of things, it's possible. So let's see, I think I have the normal distribution here. This is the formula that goes with it. Let's see, what are the interesting things to mention about this? First of all, it's completely symmetrical. It looks like a hump. Here you see that, well, if it's defined like this, the middle part is exactly there with the 0. And if it looks like this, then typically what you have is that almost all of the cases are between, let's say, -2 and +2. This formula, also quite interesting to see, also why the normal distribution is of interest, has only 2 parameters. Here, mu, that's actually this value over here, so in this case mu is 0, and sigma, that is how wide this thing is. So the nice thing about a normal distribution is you need only 2 parameters and then it's completely defined. Here's the middle, this is how wide it is, that's it. Then you exactly know what it looks like. Nothing else that you need. Okay, again, if you would know something is normally distributed, great, then we can do math on that. But we have these empirical distributions that we have to deal with, so we need a trick. Okay, again, theoretical, fine, that would allow probability calculations. Yeah, let's press that. Now, just to, the coin toss example is as boring as you can have, but it is the easiest one that we have to show the whole idea behind it. So let's nevertheless try to go through this one time. Okay, I'm what is it? Tossing a coin 1,000 times, and I want to figure out if it's fair or not. If it's fair, it would be around 500 times heads and 500 times tails. And let's suppose that I get, well, let's say here, 525 times heads. And I need to decide, okay, is this thing really fair or not? Okay, easy thing to do would be, and here you see this data code, you don't see it from there now, but if you have the slides, you can easily see that you can do this in Stata if you want. You simply do it, you simulate the whole thing, and here you see what eventually happened. What I do is I throw a fair coin 1,000 times, and that I do 10,000 times. So here I found my, where is it? 525. That is what I found. And if I do it 10,000 times, then I would get this. Okay, so now I have to decide. I found 525. Let's make it a bit more extreme. It's easier to get the idea. Let's say that I found 570. Well, if I do this, 570, that for a fair coin, that would be really rare. 570 is over there. So that is really strange. If I would have a fair coin and I would find 570, it's unlikely. So then I would conclude, no, my coin's not fair. That's really unlikely because almost all the cases would be over there. Or 510, another extreme, that would be about there. Then you can say, well, if I do this 10,000 times, I see that, you know, it's quite likely that you get something over there. It's quite unlikely that it's over here, nothing's over there, or hardly anything. It's even more unlikely that you find something over there. And there is, of course, the question, yeah, where are we going to draw the line? Somewhere over here, or a bit more to the right, exactly where do we do it? And the standard, basically, agreement that we have in statistics is, well, we stop at 5%. And usually, if we do not know up front, if the coin might be unfair in the direction of heads or tails, then we put 2.5% on one end and 2.5% on the other. So the last 2.5% that I find here, if I end up with my actual number in that area, then I'll say, okay, not a fair coin. If I end up over here, in the first 2.5% that I have in this distribution, I'll say unfair coin as well. If I end up in that middle 95% part, fine, I'll conclude that the coin is fair. Okay, so that's the thing that you can do. Standard stuff. You need not simulate this, you can actually calculate all this, would work as well. But the principle is all the same. We're trying to figure out, given that the coin is fair, I'm assuming something about the world that allows me to do the calculations. How likely would it be that I get the data that I have? How likely would it be to find 525? How likely would it be to find 570 or 510? So that's the thing to get from this. And we're on time. 1 minute. Yeah, just this one before the break. There are two things that you need to pick up from this in terms of terminology. One is H0, or hypothesis 0. That's typically used for the baseline hypothesis, and it has an equality in it. So here, that would be the probability of heads equals the probability of tails equals 0.5. That allows me to do the math. And then the alpha value, so the percentage that I use for rejection. Here, well, the standard is 5%, and the standard is also the 5% if you do not know anything up front about the unfairness of the coin. So it could be unfair in either way. You take 2.5 here and 2.5 there. But these two things you should memorize. Alpha, the probability of rejecting H0 when it's actually true, because this could happen. If H0 is true, the coin is fair, then we get this. And then coincidentally, in 5% of the cases, you end up there anyhow. You'll conclude the coin is not fair, even though it is. So that 5% is also the probability that you make a mistake at this time. I'm concluding that H0 is not true, and it was. Okay, I'll continue with that. Okay, here goes. Last bit. We're on our way trying to figure out how these statistical tests work. In the meantime, we figured out that there might be a bit of issue here. The only thing that we can calculate with are theoretical distributions, normal, Gaussian, log normal, who knows what, and the stuff that we have is sample-based and it's all empirical distributions, and they do not look like any of these known distributions up front. What we then talked about briefly was just to show you that the theoretical calculations might work if you have a distribution to start with that is theoretical here. We're flipping a coin 1,000 times, and we find that, what was it, 525 times or 570 times you had heads, and now we're trying to figure out, okay, is the coin fair or not? We said 2.5% on this side, 2.5% on that side, and then we can figure it out. All that we did already. Terminology, H0, the base hypothesis. That's an assumption about the world, and that assumption needs to have an equality in it. And you need the equality because that will give you something to work from. Alpha, that's the probability of rejecting H0 when it's actually true. So alpha, that was by definition 5%, and we took 2.5% on either side. And there we are concluding that the coin is not fair. Okay, that we had. Now, a little bit about the terminology here. It's easy to mix it up, and it is often mixed up, because there are only two things after you've done the testing that you're allowed to say. One is H0 is rejected, so my base hypothesis that I started with is rejected by the test that I did, or H0 is supported. And you know, if you want, you could put here H0 is not rejected, but what you cannot say here is H0 is true. So that's typically the standard mistake here. What is possible is to reject H0, but that's it. Now, why is that the case? Well, first of all, it's reasonable also intuitively. Saying that H0 is rejected, in this case that means the coin is not fair. So we start from the coin is fair, and I'm saying, I don't know what it is, but fair it's not. So that's still a rather broad statement. I still do not know what the coin is, I only know that it's not fair. And this one, if you would be able to claim here H0 is true, so the coin is fair, that in terms of information is way stronger than the other one. This is just saying it's not 0.5, the probability, and that would be saying it's exactly 0.5. And it would be weird to be able to say that, given that that one has much less information in it. Now let's see why that actually is. This is one of the reasons. Why can't you just say H0 is true? That's it. You know it now. The coin is fair. Well, it's quite simple actually. If you have something like this as H0, that's what we had. The probability of heads is 0.5. Then you can do the math and you find, let's say, for 511, 511 would be, let's say, about there. That's still reasonable. So there we would say H0 is supported. Now, if I would do the whole exercise again, but now not with the probability of 0.5, but let's say 0.51, slightly higher, then again I would get something that looks like this. It would be moved to the right a little tiny bit, but still 511 would be somewhere over there. So still just fine. So it's not only that I would have this one supported, but if I would have used as H0 0.51, that also would be supported. And 0.52, I guess, also supported. And so on. So there are way more values of H0 here that will also be supported. And in fact, what's called a 95% confidence interval is exactly that. The set of H0 values that would all be supported. And 0.51 for sure is in it here. And we'll see in a minute exactly what the confidence intervals are. You could do all this simply by increasing that value over there to 0.52, 0.53, and then at some point you'll see that indeed 511 is in the 2.5% bit. There are faster ways to do it than that, but in principle this is possible, and this is the reason why you're not allowed to claim, aha, now I know H0 is true. given that the 511 is somewhere in the middle of the here you see in Stata how you can do it immediately, figure out what that confidence interval is. Here, for 511 out of 1,000, the command is CII for confidence interval immediate. You start from 1,000, 511 heads, and you see 1,000, 511, so the mean is 0.511, and there you get the exact confidence interval. So in fact, all the values of H0 lying between this value and that one would cause a 511 out of 1,000 to be supportive of H0. Okay, so claiming if you start from H0 says probability is 0.5, that it is true would not be right because all these are also still okay as a guess, so to speak. Okay, so slowly one more time. I'm taking my time for this one because this is the basis for all the rest that is going to follow. What we have here, some kind of hypothesis. Here in green, probability of heads is 0.5. That equation there, you need it. It cannot be something, well, the probability of heads is more than half, or more than 0.7, or whatever you like to call it. You have to have something specific, because that thing allows you to either do the calculations or run simulations or whatever. Then the data gives us an estimate of the equality. The estimate for 525 would be, okay, the mean, 0.525. Here you see the calculations on the sample are easy. It's nothing. Now we determine what kind of distributions we would typically get. Okay, we can calculate or simulate that. We made that hump through simulation in Stata. I could have done it theoretically as well, but it doesn't matter much how you do it, as long as we know that it is possible. And now we figure out how often it would occur to get the data that we actually have, or worse, where worse means further away from H0 if H0 were true. So we start from, let's assume that H0 is true. We do the calculations. If H0 is true, then what kind of data could I get? And I compare that with the actual data that I have to figure out how reasonable it is to assume that H0 is true. Okay. All statistical tests have this setup. Now without the stuff in between. First, hypothesis with an equality in it. Then data that gives us an estimate on the sample itself, all easy. Distributions, you determine what kind of distributions of means you would typically get when H0 would be true. That was the hump that we created. And then we determine how often, let's say, something bad occurs, where you end up in the tails of the distributions, and we can conclude something about H0. Now this is doable only because here we have this theoretical thing with the coin flip where we know, okay, we start from 0.5 here or 0.5 there. So this looks like bad news, because what do we need in H0? That's easy. I can assume something about the world also in our data. Boys and girls are in all likelihood having the same score on that soccer quiz that we have. That would be in H0. The mean for the boys equals the mean for the girls. So we can come up with an H0. That's easy. But assumptions about distributions that we can calculate with, yeah, this is not so easy because these empirical distributions do not follow, by definition, any of the standard ones that we know how to work with. So this is what, for here, what was that? Boys and girls, who likes classical music? I think this is from last year's data set. So the H0 I can come up with. Let's assume that boys and girls like classical music just as much. Equality in there, you can do the calculations if you want. Yeah, but on what distribution? This doesn't resemble anything that is theoretically known, and that also doesn't resemble anything that's theoretically known. So now what? Okay, and now we get the, let's say the beauty of statistics in, where we will only try to realize that it is beautiful and not so much how to calculate it, because it's not so easy. It's called the central limit theorem. And this is also why the mean is so important. So you could have thought already 10 times, mean, I know what a mean is, forget about that. But the point is not so much what a mean is. The point is that we need it to do all the statistics, because otherwise we wouldn't know how. This is the central limit theorem. Here you see the difficult version, and this is, let's say, the shorthand that you could more easily memorize. Let me first do the difficult part. If you have xn independent random variates, where these x each could have a distribution, or could come from a distribution of any size, doesn't matter what. So this sounds like data. These are all data points. They have a mean, here called mu, and a finite variance called sigma squared. Okay, so each of them has a middle and a spread that you can calculate. Fine. Then this one here has a limiting cumulative distribution function which approaches a normal distribution. Okay, this is going to sound good. Normal distribution, that we know, and that thing, if we, let's say, wait long enough, so if a sample is big enough, we'll get close to what a normal distribution is. And then, if you need, if you have a couple of extra assumptions there, then what you can also show is that this thing, the average of all these separate parts, is actually normally distributed. Okay, now what's called the fuzzy central limit theorem. So without all the statistics that you really need and the sums and the who knows what, the mean of a sample, and it doesn't matter what distribution that is coming from, typically has a normal distribution. And this is great news, because typically what we want, if you want to compare means, you have girls, you can measure the mean there, you have boys, you can measure the mean there, and the distribution of that mean, not of the thing itself, but of the mean across the whole group, that will follow approximately a normal distribution. Actually, this is only true as the sample size gets larger, so you know in the end, what you'll end up with is something that looks normal. And with that normal distribution, we can calculate. So this is basically saving us for, in the sense that now we can do something with the data and come up with conclusions about the population as a whole. Although this one sounds relatively straightforward, oh yeah, this is one implication of the central limit theorem. You might have wondered, where were we? There, this thing sort of looks bell-shaped already. This is not a coincidence. Do anything here. I mean, this distribution itself was not clock-shaped at all. You know, you have 0.5 here, 0.5 there. That's it. If I do the math and I calculate means over groups, I do get a bell shape. So here you see it happening actually. This is the central limit theorem happening right in front of your eyes, so to speak. This is not a coincidence. So there you have it. This is what actually solves matters for us. Although it, not that complicated right here, to prove it is a different matter. I tried to find online a place here and there where I could actually find the proof, and the shortest one that I found is this one. Okay, this is, I'm not so sure how good you are in, well, calculus this is mostly, but this is not easy. Yeah, so this is, it's the shortest one that I can find, so usually the shortest ones are more complicated, so there might be longer ones that are easier step by step, but still, this is not something that you easily come up with if you just start with, let's say, an empty sheet of paper. Okay, but this is going to work very well for us. Oh, I had it already. This thing over there is normal, and we could have known that up front. Okay, so now back to the statistical tests. Yeah, now we can actually interpret what's in these different tests that we tried way in the beginning. So here we have, again, the chi-square test, where we have males and females over there in the rows and in the columns, if you consider yourself to be better than average. Now, the only thing we have to figure out here for each and every one of these cases is, this is a statistical test with an answer there, there, and there, and there. But the only thing to figure out is, what is the question? And the question is here, what is H0? And H0 would be something with an equality, so that would be, it doesn't matter if you are male or female with respect to the distribution across these four categories that we have. So here you would say that the distribution of these 68 across these four categories is the same as the distribution of these 35 across these categories. And again, as in the coin flip, this will not be exactly true. With the coins, you flip it 1,000 times, you will not likely to find exactly 500. So here again, it might very well be that the distribution of these numbers across the second row there is not exactly the same as the distribution of the numbers across the first row, but you have to be able to figure out if it's, let's say, far away enough to say that equality does not hold. So here H0 would be, there is no difference between this row and that row in terms of the distribution of cases. And there you find, okay, if that's H0, that's the probability there. If this probability is smaller than 0.05, then we are in the edges, and we are rejecting H0. Well, apparently we're not. This is way bigger than 0.05. So here, I'm actually finding that H0 is supported. I cannot reject equality. Same thing here. This is a t-test. We have two groups, males and females, comparing net income across these two groups. Here are all the calculations on the sample itself. Here, there are actually three of these numbers there, but let's focus on that one. What would H0 be here? H0 would be, well, males and females are scoring the same mean on that net income variable. And you see this is, well, almost true, 7.5 versus 7. And the question is that 7.5 far enough away from 7 to conclude that equality is rejected? And we find there, we'll talk about later why we choose the middle one here, that the probability is 0.488. So again, way bigger than 0.05. Apparently we're not in those parts way on the edges of the graph, but somewhere in the middle. So here we conclude, again, H0 is supported. We have no evidence to reject equality here, even though the numbers themselves are not the same, but this is close enough not to reject the difference. Same thing over here, correlation between age and the guess of income. So the idea could be the older you are, the higher you think that your income is going to be, for whatever reason. What we find here is, well, what would H0 be? H0 would be, there is no relation between these two. Age and income are not related at all. And in fact, that would be signified here by the actual correlation being exactly 0. Well, it's close to 0. The probability thing is over there. So again, smaller than 0.05 or bigger than 0.05. It's bigger, 0.79. So we're not in the edges over there. We're somewhere in the middle. We're not rejecting H0 in all these cases. Okay, so here we have it. Distribution over the categories of that variable is the same for males and females. The means for males and females are the same. And X and Y are not related. And I should have said here, because normally you define these with an equality sign in it, the relation between X and Y is 0, equals 0. And then we can do the calculations. Okay, so if you see a statistical test that you don't know or do not understand exactly what's going on there, the thing to figure out is what is H0. There must be an equality somewhere that you need to test, and then in the end, the number that you get is suggestive of that H0 hypothesis. And you can do that even without you knowing what's happening behind the scenes in terms of calculation. Okay, it took a while, but the point is that the beauty of this is we wouldn't have been able to do anything if that theorem wouldn't have been there. Then all the statistics would be out the window. There's nothing that we can do. And the only thing that saves us is, well, if you have samples that are large enough, means will be something that you can, let's say, decently calculate with. This is also why we focus on means, because if these means are there, we would compare means across groups and not something else. Then we know what to do. If we would have wanted to compare, let's say, the modes across two groups, it would be way more difficult. By now it's possible, but all the statistics need then of a different kind, so to speak. So this is what's actually saving us and allows us to do all the tests that we typically have. Okay, so this was what I wanted to get across today. First of all the data are typically samples, and none of the samples are interesting in their own right, because you want to make conclusions that are about the population as a whole. So that you need statistics. The sample itself, easy. That's what I said. All the statistics, so the things that I talked about, you know, bell-shaped, over here and over there, and 5%, and 2.5 here, and 2.5 there, all that, and mu and sigma, all that only plays a role for inference. If you want to know something about the population, if you want to know something about the sample, or if your sample is the population, if let's say the only group that I'm interested in is the group that we are surveying right here, then I need no statistics, I simply have the answers in the data itself. That's the difficult part. Then, all tests have this setup. This you should simply memorize until you have this, really memorized by heart. And this one's relatively easy, and the difficult part of the course is that there will be more things of this kind, and as this stacks up over time, you have, let's say, 8 or 9 of these things that you need to have in your head, and then it helps you understand what's happening, instead of relying on that you have actually memorized all these separate parts. Because it's easy to mix up, was it below or above 0.05, and was it 0.05 or 0.5, or was it 0.95, and you mix all that up, you do not know what you're doing. Okay, define H0, check your data, calculate or simulate how likely it is to end up with your data if H0 will be true. The good news about that is you do not need to do it. That's being done by your statistical program. Conclude, if the probability value there is smaller than 0.05, then you reject whatever your H0 was. And confidence intervals, typically 95% confidence intervals, are the values for which H0 is not rejected. So that's how all these statistical tests work, all of it. And the central limit theorem is helping us to be able to do that. And if we wouldn't have that, then there would be nothing. Limit theorem would take a while, yes. Okay, so given that, all tests can be understandable. You might not exactly understand what's going on behind the scenes, but what it is that is being tested is relatively easy to figure out. Simply by trying to figure out what H0 is going to be, even for tests that you have never seen before. Okay, for this, because this was the last slide, I've put some material online to practice with. You should be able to do most of these, or I think even all of those. As soon as I know something about the quizzes and exactly where we're going to take the next one, I'll let you know. If not, we'll try to, plow ahead with whatever that we can get, and then it will be next Friday. Otherwise, I'll let you know. See you next week.